Alrighty, welcome to the last video in electricity and magnetism, the only video about magnetism. Yeah, it's a pretty short section because magnetism is such a nebulous concept, but here we're going to relate magnetism over to electricity. And I'm going to start much like I did when I was talking about the electric force and using an example to talk about the magnetic force. Let's think about a magnet. Right? Get a magnet bar, right? If you move another magnet close to it, the magnet bar starts to rotate. Why does it start to rotate? Well, because we've got one end, the north end as we call it, and the other end, the north end, and the south end. The south end likes the north end, so it tries to rotate over. And the north end likes not to be next to the north end, so it rotates the other way. It's the rotation of a magnet. That's what we've established about magnet. One end attracts and another end repels, just like our buddy the electric force. If we put a magnet on the ground at Earth, one end would always face north, right? So we call that end the north-seeking side. And we call the other end, because it doesn't point north and because the other one's pointing north, it has to point south, we call the other end the south-pointing side, the south-seeking side. Right? Yeah. Now, if we were to put a magnet in a field of magnets, oh gosh, a magnet field of magnets. Let's draw another little magnet stick. It's got its north side and its south side. And we were to draw field lines, because magnets also have field lines. The lines would look something like this. It's more like field dashes when it comes to magnets, honestly. Kind of go out. Over here, it kind of curves over. Might be a bit of a bigger curve there, but it's going to go out, go out, go out, and start to curve over in these big overarching arches, right? That's what the magnetic field looks like. And as we can see by these lines, the magnetic field is particularly stronger. There are more little dashes around the poles, around the ends. And they're kind of less dense. There are less of them throughout the sides. So the density of these magnetic field lines shows the strength, and that is called magnetic flux density, which is kind of like electric field strength, but not quite, because when you think about electric field strength, light, it's a uniform strength all around, right? If you've got one here and you've got one the same distance away here, it's going to be the same strength, but that is not true for magnets. If you've got a magnet placed here, it's going to be attracted a lot. If you've got another magnet placed over here, same distance away from the magnet as this one, it's going to be attracted a bit less. So magnetic flux density is kind of unique in that aspect. Now, just an interesting little tidbit. Opposite poles attract, right? And so if you were to draw the magnetic field lines of the Earth, right? Kind of sneak around these big loops. The kind of form when you get magnetic field of the Earth. Because our north-seeking end always points north and opposites attract, that means the north geographic pole actually is a south-seeking magnetic pole. Kind of ironic, isn't it? So the Earth is like a big magnet. We've got a south-seeking pole at the top and a north-seeking pole at the bottom. So, given that, with magnets, we can create the same sort of, if we were to have one side that's north here, one side, two planes, one's north, one's south, we could create a uniform magnetic field. Right there, right? And so that's another similarity between the magnetic field and the electric field, but it gets really interesting when we consider the magnetic field around a current. So you've got a wire, it's a vertical wire, and you've got a current going up through it. That current is going to create a magnetic field that rotates in rings around it. Yeah, that's what it's going to do. And so a simple way to remember this is if you curve your hand, kind of like that, the current is going to be going in the direction of your thumb, while the magnetic field goes in the direction of the curvature of your fingers in kind of a circle. around your thumb. So that's a quick and easy rule for remembering the magnetic field around a current. And so now, we talked about this. So we know that the strength of the field is related to the density, as I discussed earlier, of the field lines. And that means the magnetic field is stronger close to the poles. And so, once again, that's magnetic flux density. Let's give it a variable. The variable is B, because we haven't used B for anything yet. Now, what if you took this current, this wire, and you folded it into a coil? You fold it into a nice little loop-de-loop, right? And you made a loop. Well, if you think about it, because magnetic field forms little loops around, right? The poles here of each magnetic field, these ends here are all going to combine to make it really powerful in the center, which is going to create a movement right there in the center. Right? Now, what if you do it inside of a solenoid? What's a solenoid? Well, a solenoid is just a bunch of those rings. Kind of looks like that, right? Well, then you start to get something that looks a wee bit like a magnetic bar with lots of lines going in and out, and the ones at the ends curving back around. So, based on this, the current is causing the creation of this magnetic field. We can determine that magnetism is caused by the movement of charges. That's important there. Magnetism is related to electricity because it's caused by the movement of charges. Now, we've discussed how magnetism affects other bars, right? But what about the force that magnetism exerts on just a straight conductor? We talked about the solenoid, right? The curvy-wurvy solenoid. But what about that straight line that we were talking about earlier? What if you put it on a magnetic field? Well, it's going to experience a force perpendicular to the field it is in. So if you have the current that goes this way, and you put it in a field that goes like this, these are the lines of the magnetic field. Well, I can't necessarily draw it because this is two-dimensional, so I'm going to have to redraw. Let's make this a three-dimensional drawing. You got the current going across like that. Then perpendicular to that magnetic field, you're going to have a force. There's your force, there's your current, right? Using that, we can relate the force, the field, and the current with a formula that we call Bill, because that's what it is. The force equals the magnetic flux density, which dictates the strength of your field, multiplied by your current, multiplied the length of your piece of conductor. That is how you determine the force of magnetism. And using that, well, we've got newtons, we've got amperes, we've got meters, but we don't know a unit or anything for magnetic flux density. So let's recalculate. We know that magnetic flux density is equal to force over current times length, which is newtons over coulomb meters. If you were to simplify that, you get kilograms times meters per second squared multiplied, because dividing is just multiplying by the inverse, right? Multiplied by coulomb. Oh, well, it's not coulomb, sorry. Ampere's there. Ampere, which we know is a coulomb per second, right? We switch around. We get seconds per coulomb meters. 1 second cancels out 1 second here, 1 meter cancels out 1 meter here, and you end up getting kilograms per coulomb seconds. That's the unit, a kilogram per coulomb second, which is funnily named the Tesla. That's the unit of magnetic flux density, the Tesla. And if you want a non-unit definition, a Tesla is simply defined as a flux density of 1 Tesla. 1 Tesla causes a force of 1 Newton in a conductor of 1 meter with a current 1 ampere. And this brings us to an interesting concept, which is defining the ampere. Because I've already told you that the ampere equals your charge, or the coulombs, per your time, which is second, right? However, it is incredibly difficult to measure that practically in actual experiments. So there's been a push to define it like that in practical experience, but the way that we define the ampere now is in terms of this magnetic force. Think about if you have 2 conductors with current in them, right? And what's happening here, current going one way, the currents are going the same way, the currents are equal magnitude. If you were to look at it from above, push that up there, the field goes out it in circles, goes out the same way in circles, right? And you get an equal force going towards either one, right? So the ampere is defined as the current in either of these wires, the current that would cause a force of 2 times 10 to the negative 7 newtons. I know, it's kind of weird. Per meter in 2 long parallel conductors separated by 1 meter. And that is the technical definition of the ampere. Kind of like how the technical definition of our buddy, the kilogram, is that one silver guy sitting in the bottom of the vaults in France, right? Yeah. So, out of defining units, let's head back to that magnetic force. We already know how to calculate it, Bill equation, right? But how do we determine its direction? Well, there's a simple rule called the Fleming hand rule, where you put your hand like this. Your thumb up in the air, your index finger sticking out, and your middle finger kind of sticking that way. This, your index finger, is the direction of the field. It goes this way. Your middle finger is the direction of the current. So that means your wire, your current are going like this. My pen is the wire and the current. The field is going across it. And your force is your thumb, perpendicular, pointing up in the air. Just like that diagram I drew there. And that's an easy way to determine the direction of the force, because force is, of course, a vector. Now, what if your field is weird? What if you're using Fleming's hand rule, except your index finger is janky and it's pointing this way, and you've got a non-perpendicular field? Well, it's pretty simple, because that's why we have field lines, because they're vectors. If you don't have a perpendicular field, you've got your current going like this, and there's your field, and you've got your angle theta between them. You just find the component of that field that fits. Like, let's say this is B. You're going to make B your hypotenuse, right? You're going to draw a line. This line right here, that's going to be a right angle, that's going to be perpendicular to your current. So that's the opposite, that's the hypotenuse. B sine theta is going to be the component you're going to use in your Bill equation. And that's pretty simple right there. But now we're going to really relate the magnetism and the electricity and discuss charges in magnetic fields and how they behave. All right, so we know that the magnetic field is caused by the movement of charged particles moving through a metal, right? And we know that the force caused by it is F equals Bill. Well, what's something else we know equals current? Something we can equate. How about that thing from way back in the beginning? The NAVE. Let's insert that in there for our current, because that's going to help us relate to a charge, or more specifically the electron, the fundamental charge, right there. There it is. Yep. Now, this can also equal BNEV, where N equals the number of electrons in the wire, right? Because the N is the number of electrons per unit density, and the A is the area, and the L is the length, area times length is volume, and that's the number of electrons per unit volume, so those all combine to make the number of electrons, which is n. So you just replace them all with n. And then, from B nev, you can determine that the force is on each electron, you now know, is going to be on all the electrons is B nev. That's the overall force on all the electrons. But if you just wanted 1, well, you just divide by the number of electrons. And the force on one electron is going to be Bev. This is our Bev equation. We got Bill and we got Bev. Yeah, the equations are fun in magnetism. And now to make it less fun, that's the force on one electron. But what about the force on any charge? Well, you just replace that fundamental charge there, electron, with whatever charge you want. So the force on any charge in a magnetic field is B for flux density, Q for your charge, and V for the drifts of that charge, the speed at which it is drifting through your conductor. Bam! Pretty simple. Now, on a charge, because the magnetic force is always perpendicular to the motion of the charge, it's going to move in a circle. Why? Well, if you think about it, you got your charge here, it's moving this way. The force is perpendicular. It pushes it down this way. So the movement combined with the force creates a path that kind of looks like this. Once you get down there, now your charge is moving this way. The force has to be perpendicular, so it goes like this. And it starts moving like this. You see where I'm going like this? It's moving here, up, moves over there, moves over there. And you've got a not so perfect circle, but you get the idea. Circular motion. So in this case, you can see that the magnetic force here is the centripetal force. We know centripetal force is mv squared over r from our circular motion section. Because that is equal to magnetic force, we can equate it to our bqv. And if we wanted to solve for radius, our radius would equal mv over bq, which means that if magnetic flux density, charge, and mass are all constant, which they most typically are, the radius of the circle is proportional to the drift speed. So if your charge starts drifting slower, it's going to start drifting in a smaller circle. And that is actually how we accelerate particles at CERN. What we do is we keep them moving really fast, so they move in a very large circular path, and so the large circular path that is CERN, you know, the big collider, in a magnetic field, and make them collide. Bam. And the idea is the same with the non-perpendicular fields with charges as it is with the long current wires. It just use the component of the field that is perpendicular with your charge's motion. And that's it. That is all for electricity, and that's it for all of year 1 chemistry. We'll make some videos on year 2 chemistry next year. Be sure to join us then. See ya, fellow physicists.